Good afternoon, I'm Mike Duigou. I'm a software engineer at Liquid Robotics. We build ocean-going robots that do data acquisition at sea, both for commercial, scientific, and military applications. These are sea kayak-sized surface robots. They're not the diving kind. And the reason is because they spend literally months, or in some cases over a year at sea, collecting kind of environmental, weather, fisheries, scientific. We even look at volcanoes and that kind of things, as well as submarine detection, marine patrolling, and we also act as the surface uplink for some of those subsurface vehicles and subsurface stationary sensors. Now the robot, it's semi-autonomous and often very remote from where it's being piloted. These can be almost anywhere in the world, as high as 78 degrees latitude to the equator, and kind of everywhere in between. And it has to be pretty much self-sufficient and entirely reliable. Just going out and flicking the power switch is not an option in most cases. Now, prior to working on these robots, I worked at Oracle, and before that, Sun. That's where I got the kind of robotics bug at. I originally started working on server software, the Juxta project, which was Sun's peer-to-peer effort, and we were building things that were much like servlet containers for executing software. So we had the same perspective that something like a servlet container or Netty or Jetty would have, in that we had to be highly reliable regardless of the quality of the code that we were running inside the container. I also worked on the Java 8 team and a variety of projects like the Stanford Audi autonomous car and various industrial robotics and Java 1 demos like dancing robots. So what we're going to be talking about is durable systems. These are systems that must function for as long time as possible, even if errors do occur. And some types of failures can be anticipated, and you just have to continue to work in spite of those failures. Kind of get as much functionality out of a run as possible without ever rebooting, rather than, if there's any kind of fault, just restart over and try again. And we'll start off with a brief tragedy. This is a little episode that occurred in 2008 with a customer that we had at Sun at that time. And these guys were trying to modernize glass manufacturing. So up until that time, if you built a plant for producing sheet glass, it was done using traditional ladder logic PLC, which is essentially the same technology that ran trains in the telegraph era. So they were trying to move technology forward by about 100 years and produce something that could be replicated more easily to produce many more glass plants if they wished. And this was a pretty ambitious project, but during the first week of deployment, they had a bit of a disaster. The way it worked is that past any given point in the assembly line, there were 170 sheets of glass that are 2 meters by 3 meters each passing. So these things are moving pretty quickly. A single gap sensor that measured the thickness of the glass and adjusted some wheels that touched the glass to accelerate it, change its direction, etc., failed. And unfortunately, this caused a whole pile of glass to pile up in one place, which resulted in 5 weeks of downtime just sweeping up broken glass, and then a couple of months to figure out what went wrong and to put the assembly line back in production. And because it happened in the first week of deployment, this didn't exactly cause a lot of confidence. So what broke? This is the code of the one of the threads that was running in the application. Now, Java real-time was a little different than the Java you may be used to. It would be actually composed of many real-time threads, all of which had the same pattern, where they would do some activity and then wait for next period. And then 2 milliseconds, 20 milliseconds, 200 milliseconds later, they would be run again. So it spends most of its time actually sleeping in this wait for next period method, and then runs again at a very predictable time as often as it needs to. And the loop is to read the sensor and then adjust the gap based on that reading. And it just runs forever. When you want to shut down one of these glass plants, you just stop injecting new glass into the beginning of the operation. When all glass has exited the assembly line, you shut the power off. There's no normal shutdown procedure for this, so it just runs forever. So what actually broke? Well, in that read sensor routine, this is the code that they had. It wrote out a carriage return saying, I want to know what the sensor reading is. And then it read back the reading from the sensor. This is a fairly standard, simple serial protocol. And then it parsed the result of that. On the other end of that was an embedded sensor which was outputting the thickness values. And its values that it was outputting were effectively equivalent to this C printf statement, %4D. So it's a 4-character integer followed by a carriage return. And this worked perfectly fine in normal operation. You see values like 1085, 1061, 1094 come back. But then very unexpectedly, they got a value of 978. Well, integer.parseInt doesn't like spaces. And it failed completely. And through a numeric format exception, which is a subclass of the legal argument exception, aha, they caught that. And they printed it out so that when it occurred, there was a printout of the numeric format exception. However, the reaction then was to throw new error, sensor read failure. Now, what did this do? Well, in their main loop, they had been catching exception. Error is not an exception, so that this thread died completely and was never executed again. So the gap sensor stopped adjusting, and that's why it caused glass to pile up. So how did we fix this? The first thing to do was change the catch of exception to catch throwable. And they also, of course, fixed the read sensor method so that it parsed integers correctly. It also now, instead of running just in a loop of executing the wait for next period, it now runs that in a finally clause. So no matter what exception is thrown, it will actually continue to run. So you may lose a single iteration of this loop if there's some error you didn't expect, but for the most part, it'll just continue to run. This is the durable part in that in the presence of an error, it attempts to function anyway. Some bad things could happen, if you miss one period due to an error, but it's probably better to keep trying again rather than just give up and quit. So, we've talked about why or what went wrong. Why did this go wrong? Well, they were mechanical engineers. They had very limited experience with Java APIs. This whole Java and Java real-time was entirely new to them. They developed their code from samples rather than specifications, so they only had access to what they had seen the center output. They had no idea what the printf format statement was. That wasn't something that they thought that they should share between the projects. They just looked at what the sensor did and tried to match that. They didn't really handle the errors properly. Throwing error in response to the handling of that illegal argument exception wasn't a great solution. And they didn't really have any unit testing. They weren't testing any boundary conditions, any kind of illegal input, and they didn't do much integration testing. All of these things, were later fixed down the road. We introduced them some more best practices of how to build software for mechanical engineers. But in the end, the project was a success. And if you were to, go to modern glass factories in Europe today, there's a good chance that it'll actually still be running on Java. It's now running using the Jamaica VM, which is the successor to the Java real-time VM. So what are we going to talk about? Are these opinions just my opinions, advice, rules? Most of this stuff is coming from the robotics industrial automation viewpoint that I've been working in. But it also applies to people who are writing any kind of highly reliable software. Things like containers, Netty, Tomcat, anything that has to run for a very long period of time, regardless of the quality of the code that's running within that container. And the main things that we're going to talk about are consistency, predictability, and discipline. They're not necessarily hard rules, but they're applied in a regular way. If there are exceptions necessary, you just document them and continue on, and hopefully learn something from that case. We kind of intentionally try to avoid ritual practices where we do something because we've done it all that way all the time, but don't really know why. Most of the things that we say we do, we have a reason for them. And we'll go through some of these examples of the discipline that we do. So with regard to throwing exceptions, for example, we don't throw bare exceptions like runtime exception, error, or throwable. Instead, we generate subclasses of exceptions. That's not something that a lot of people do. They'll throw illegal argument directly. Well, you can make a subclass of illegal argument that both gives it a more relevant name, and you could also improve the formatting of that exception to include the data that was bad, for example. Go beyond what you get from the base exception types. And definitely don't do subclassing via messages. I've seen a lot of cases where people will throw an illegal argument exception with a particular message and then up the stack actually compare for that message. That's just kind of insane. Why not make a subclass and then you can use instance of or catch that particular subclass if that's what you're interested in, rather than matching on a name. You can declare runtime exceptions and errors on your throws exceptions. Normally, people only declare the checked exceptions that they have to declare on their throws. But if you notice, the JDK will document that it throws null pointer exception, illegal argument exception. That's not necessary, but it sure is useful, isn't it, to know what exceptions are going to be thrown. And in the case of the JDK, that's actually how they build the JCK. The people who build the JCK actually look at those exception specifications that are on the methods, and then they test that the exceptions are thrown when they're supposed to be. They'll actually pass in the null parameter and see if a null pointer exception is thrown. So it has a great documentation value and specification value, even if it's not absolutely necessary. So we talked about throwing exceptions, now about catching exceptions. Like Pokemon, you should be catching every throwable. And the key is, it depends on, based on the type of exception, where it's going to be caught will vary. But you should at least have some idea, no matter what exception is thrown from a particular piece of code, where it's going to be caught. And you should always be providing a backstop, so that if you didn't have some other handling for the exception, it ends up being caught by that backstop. And in most cases, that'll be at the outermost layer of your thread runnable, or in your Lambda, where you catch everything just to make sure that it doesn't actually escape the method. And in the case of threads, you can also register an uncaught exception handler. If you're catching everything with a backstop like this, that's not really necessary. And in fact probably provides inferior logging to what you'll do in your try-catch throwable. But having something to catch uncaught exceptions is definitely a good idea. And if it's a truly exceptional event, not all exceptions that are thrown are all that surprising. You don't need to log literally every exception thrown. But if it is something that's truly unexpected, you should definitely be logging it. So what about uncaught exceptions? What happens to them? In the case of a thread, it does go to that uncaught exception handler, and the thread is stopped. but other threads continue to execute unaffected. If that thread was doing something important in your application, well, it's just no longer doing that function at all. And we'll talk about ways to mitigate that a little later. Other cases, timer task, the same thing happens. And it doesn't really continue except for one weird case, which is interrupted exception, in which case it'll still continue to run timer tasks. The really tragic thing about timer task, and this is one of the reasons why almost nobody uses timer task and has moved to executors and scheduled executors, is that it also kills all the other tasks in that timer, which is really bad. Timer tasks also have only one thread per timer, so you can't execute any of the tasks in parallel. There's a lot of reasons to use executor, scheduled executor instead. Future, which is what you'd use from an executor execute method, if it throws a unhandled exception, that exception winds up as a execution exception. When you try and get the result of that future, it'll instead throw an execution exception. But there's no other effect of that. You didn't do any damage to the executor pool. All of the other executors that are running simultaneous on that pool are unaffected by your error. So it's not too bad. Scheduled future is kind of like regular future, except that it has one kind of very tricky, scary bit, which is that if you were expecting your scheduled future to continue to run, that's not the case. If you look at Stack Overflow, you'll see this is very surprising to a lot of people. It's like, oh no, my scheduled future is not running anymore. Why? Well, it threw a unhandled exception a couple of minutes ago and is no longer being executed. So if you actually had a backstop where you did a catch throwable of everything in the top of your runnable or callable for scheduled executor, you would in fact be able to continue to run because you wouldn't have allowed an exception to escape from your scheduled future. There's another case where you have to worry about uncaught exceptions, and that's with callbacks. In this case, you're the one who's handling the exception and somebody else is throwing it. So if you have any kind of case in your application where you're providing a callback interface to other people to register to have code run when some event happens, you have to worry about this. And other people's code, definitely worse than yours. It's true. Except for that guy that wrote that code 6 months ago who was actually you. Him too. So callbacks will throw exceptions that you're going to be required to handle. And this kind of backstopping approach is necessary there as well. You can't just let the callback exception kind of kill the whole thread. So here's an example of a listener interface where I've got a bunch of listeners registered and some event is occurring and I want to notify all the listeners of that event. Well, I wrap the call of each of the listeners with a catch throwable, and if the listener fails, then I'll throw out a log statement. We can improve the handling of this in a variety of ways. First off, I called toString on the listener, which may also throw, which would be bad, because then I wouldn't have caught that exception. But other cases, maybe I want to remove bad listeners. I could also support weak listeners, such that they don't have to deregister. When their code goes away, the listener automatically deregisters because the weak reference to their class is removed. You'll see that in a lot of cases where the only reference to some piece of code which is effectively dead is a listener that's held by somebody else. That's a kind of an unfortunate situation. And if you're truly paranoid, you can also run the listener rather than executing it in a loop like this. You could actually execute the listener on a separate thread using an executor. In our libraries, we actually have a combinator that takes an executor and a runnable and allows you to wrap a listener as you're providing it to the registration interface so that listener is run asynchronously. if you run them, everything asynchronously, that can kind of end up being a lot of overhead if it's not really necessary. A lot of listeners are pretty small, so it's maybe, if you're in a fairly closed environment, it's reasonable to let the person who's registering the listener decide that. Now, about removing bad listeners, what if the listener is failing because of some transient behavior like the network connection went away? Well, it might be back in a few minutes. So you're going to have to decide on policies like whether you should remove listeners that fail or leave them intact. This is a style that has always bothered me, and it's unfortunately very common within a lot of Java programming communities, which is that I have some method, and if that method is passed a null argument, well, it just returns null and pretends that the method never happened. Typically, this is kind of ignoring a bug. This is kind of like well, I don't like to pay credit card bills, so I don't pay them. You can't just pretend the method didn't exist. If this was some important method like set user credential, and you just ignored the fact that null was passed in, you've now got the incorrect user credential in place. And hopefully, you don't also allow this kind of situation to get the system state into one that's otherwise not achievable via normal method execution. If the method is not one that's mutative, like let's say something like printing out the object to the console, maybe it's acceptable, but if it changes the state of the object, you probably shouldn't be ignoring the error in this kind of way. And maybe the second sin of this method is that it kind of spreads the contagion a bit by returning null in this particular case. And a way to think about null is that it's an informal exception. Exceptions are used for uncommon or any kind of exceptional behavior for uncommon events. And null is kind of like that in that you have to give it special treatment like you do with an exception, usually comparing against null rather than catch. And it's really only informal until you try and use it, in which case you get a null pointer exception, and ta-da, you have a real exception now. Generally, you should be using a style that attempts to avoid null as an informal exception. That would be things like returning rather than returning null. As a result, if it's supposed to be a list of things, return collections.emptyList. There will be cases where you can't return some vacuous result like collections empty list, but in that case you should be throwing a real exception rather than just pretending the event didn't happen. So runtime exception is kind of the next class of exceptions that's thrown, and they're the bulk of exceptions that are thrown within most applications. Stylistically, you should be looking to catch these as close to the source as possible. The reason is that the context in which the exception was thrown is kind of the most important thing about the exception. If it's a parsing of an integer, what string it was trying to parse or what the environment was or other variables were at the time it was thrown is the most important information. And you should, you'll hopefully have that information in context when you want to print out the log statement for that particular exception. And again, catch those more appropriate exceptions subclasses rather than runtime exception itself. I would say that in a lot of cases, generally catching runtime exception is kind of a smell test, that it indicates that there's probably insufficient handling of runtime exceptions within the, or particular runtime exceptions within within that block. That if you've gotten to the point where you're catching runtime exception, There probably should have been more specific handling somewhere inside there. And I mentioned that you can declare the runtime exceptions in your throw specification. If you're not doing that, the undeclareds are effectively unhandled. You shouldn't really expect that anyone is going to provide handling for a runtime exception if they haven't seen evidence that the method throws that particular exception. If they saw it in the documentation, they might put in handling. The only other alternative is to actually have encountered it in the field. And that would be exactly the case in that glass manufacturing plant. That's the terrible way to find out that, oh, I wasn't catching that exception? Oh, well, just start over. How many millions of dollars have you wasted just to find out you needed to be catching illegal argument exception? Probably a bad approach. With regard to your own code, you can find the places where you're not catching runtime exceptions appropriately by looking at the unit tests. If you see that given runtime exceptions aren't being thrown in your code coverage, then you can probably surmise that they're not being handled as well. So you need to generate additional tests that cause those runtime exceptions to be generated so that you can ensure that you have full coverage in the catching side as well. External libraries are more of a problem. So if you're currently using version 2.0 of some library and you think you're catching all the runtime exceptions that it might throw, well, they might catch you in version 2.1 with a new anticipated runtime exception. That's where it's going to kind of depend on your audits for deciding the quality of the libraries that you're using. And choosing to upgrade libraries somewhat more cautiously with the expectation that the exception behavior of that library may change between versions in ways you didn't anticipate. We actually ran into that with Zookeeper. During the life of Zookeeper, the people who maintained it changed quite a bit. There were some people who originated the project, and then later on some people came on that were working to scale it and make it a lot more robust. Well, the behavior of the library changed significantly, even with point versions, and that caused some rough times for applications which were trying to use that library. So you got to be careful about that with some of the third-party libraries. Checked exceptions are something that a lot of people hate, and it's usually because they're required to handle them. It's become popular to kind of hate on checked exceptions. And I thought it was interesting when I joined this particular project in that the original founder of the project was James Gosling, and his use of checked exceptions was kind of more a little different than the way that the general community handled them. He handled checked exceptions a lot more like runtime exceptions, and then he caught them a lot closer to the source of the exception than otherwise. So you didn't see a lot of cases where you had to propagate the checked exception out of methods. That unless it was a kind of wrapper method or some kind of transformer or utility method, things rarely ever threw checked exceptions because he wanted to handle them fairly close to the source that they were generated. And kind of as a general rule, the person who should be catching the exception is the person who holds the resource involved. And kind of how you're using that resource provides kind of guidance as to where the handling will be. If the resource is held on the stack, it's probably a private method, and it should be handling the exception locally. If the resource is held in a field and shared with lots of things, it should be handled in the API method that the outside application is in fact calling. And kind of the goal for handling of checked exceptions is whoever is the one handling that checked exception is the piece of code that's responsible for either retrying the operation if they think that it can succeed again, or trying something else. If neither is working, then the result is not just propagation of that checked exception. It's more that you throw a different exception or some other result saying, the internet's not available right now, I can't download your URL. Don't just rethrow the, couldn't load this URL unknown host exception. That's probably inadequate context for the higher level of the application. You can throw something better. So other exceptions that might get thrown that you're going to have to catch, we mentioned that we're having backstops, so we have to catch everything at some point. These are generally something you can catch, but not a lot that you can do about in some cases. Stack overflow and out of memory are ones that can generally be handled, and there's some particular techniques for handling those. The reason these occur is generally, in the case of stack overflow, is unlimited recursion. You're not going to get an application which is generating a stack overflow using legitimate behavior. Maybe, I don't know, some web framework might do that. But in normal code, it's really hard to get a stack overflow without having recursion involved. But it can be possible to recover from that stack overflow. The key is to make sure that your code doesn't die as a result, which is why you're catching stack overflow specifically in some cases, or just letting your backstop catch it and logging the error and continue. The same with out-of-memory error. It's rarely an actual out-of-memory error. It's more likely an arithmetic error where somebody is, not handling it, something underflowing or overflowing, and now they're asking for 40 terabytes rather than 4K. And of course, the VM can't cope with a 40 terabyte request. Well, maybe some people's could, but then they'll fail just as much with 50 petabyte request instead. So it's a code error rather than a systemic error. And in the case of things like those listeners, where we were catching the throwable, there doesn't need to be any further consequence of that. The listener will probably work fine next time. And we don't need to kill the listener just because it threw this scary stack overflow or out-of-memory exception or error. Linkage error can come up, but this is something you usually notice as soon as you launch your application. You'll see either no class def or no such method error. There's a few other varieties as well. These are the result of generally compiling your code against one version of a library and running it against another, and then the methods have changed. And this can actually happen with JDK as well, where you compile against JDK 8, and then in JDK 9, the method signatures change, and the code no longer executes because it's looking for a method with a different method signature. Exception and initializer is something that can happen at kind of at any point in your program, but it generally has the same cause, which is that somebody's trying to initialize a class and something bad happened in the static initializer for that class. Unfortunately, I've seen code that did things like try and load graphics from the internet from a URL, like the icon for this class, in a static initializer for that class. And then it just failed because there was no internet connection available. The tragic part of that is that you only get one shot at it. No one will attempt to reinitialize that class again until the application is restarted. So it's generally a good idea to avoid doing anything other than the absolute bare minimum or anything that might potentially fail in static initializers. you'd think that this is something that would happen only early on in the startup of the application. Well, these things just love to lurk. So if you have something like a periodic report that runs once a month or every 2 weeks, well, it now happens only after 2 weeks of operation of your application when it tries to load a class that generates that report and needs a GIF that is hosted on github.io. Well, terrible idea. Assertion error is something that you shouldn't normally see, or in that it's what's actually thrown by the assert keyword. We, however, encountered a library that decided to throw assertion error, which we thought was extremely rude, but it's something that you should probably anticipate seeing occasionally in your global catch throwable. And some people do, in fact, throw error and throwable directly. Probably a bad idea, as we already said. You should be subclassing your exceptions so that throwing a bare throwable or error is also extremely rude. So summary of kind of catching exceptions. You should be doing it in the same method or the caller for both the null pointer exception, informal, as well as runtime exception. Check exceptions at whoever's holding the resource. An error and throwable and all those other weird ones, like assertion error, at the backstop. Whether that's the backstop on the thread or your runnable, or the one around places where you're invoking external code like listeners. So there's lots of problems which are non-exceptional, and we're going to talk about some of those now, things like how to handle concurrency, etc. The main strategy we have for handling concurrent behavior is to separate computation from mutation. This also helps for testing as well, in that we can test the computation methods directly without having to involve the mechanics of how the application state is maintained. So this has become an increasingly popular style of programming in Java, and we, like everybody else, have kind of adopted it as well. And the main idea is that what we're trying to do is, when we do mutate the object state, we do it in a way that's such that it's impossible to result in an inconsistent state on the object. So this means we don't have to do long periods of locking while we adjust the state of the object. We do some computation, and then when we're done with that computation, assuming that it succeeded, we then swap in the new state for the old state, and everything continues merrily along. And we do that mutation atomically if at all possible, generally with atomic primitives, but in some cases synchronization is necessary as well. And in this particular style, this is where it becomes possible to avoid or to handle things like those out-of-memory error and stack overflow exceptions. The only thing that you lose in this particular case is the state of that computation. Your object is not damaged by the, oops, I threw a stack, I had infinite recursion. Who knows what state the object is in. The only thing, you just throw away the bad computation and hope it works better next time. You've already got existing state that you can continue to run with, like that gap sensor, until you can retry the computation. So I mentioned that we do still use synchronized in some cases for mutation or for handling concurrency when we're doing mutation. We have particular policies that we follow, like avoiding blocking on API threads. So someone calls one of our synchronized methods or any of our API methods that we provide to other abstract areas of the program, we don't block on those methods at all. If there's any synchronization or concurrent behavior, it's just for atomicity or ordering, or something like hash map remapping where there's an amortized cost, but we don't just arbitrarily indefinitely block. That makes it much easier for the caller in that they know that they don't have to spawn off another thread in order to make sure that they don't block on their thread. And similarly, we also avoid calling APIs that might block or lock while we're holding any locks of our own. So if we're holding some lock, in order to provide that guarantee to the people who call us, we don't call anything that might block as well, at least on API threads. So, some general practices in this area would be, don't synchronize on anything you don't own. You do see people who do things like synchronize on integer or string. Why are they synchronizing these objects? They don't own them. Only synchronize on yourself or some sub object that you hold, and in most cases those would be private, for finer grained locking. If you do need to do blocking, things like I/O or other operations which may block for an arbitrary period of time, do that on a separate thread or on an asynchronous future. If it's something long-lived like consumer queue servicing, well, that's a separate thread kind of thing. If it's an asynchronous operation that's kind of a one-shot, like upload these results, do it. That's where you'd use a future instead, but you don't do it on the API thread. As I mentioned, we also we do use the Java util concurrent atomics a lot, as well as things like concurrent hash map, as an alternative to synchronize, mostly for performance reasons, but also because they're kind of more ergonomic. Java 8 does make it a lot easier with the new operations that were added on to concurrent hash map, like compute if absent, compute if present, etc. I can't believe the number of cases where I saw, well, I'm using concurrent hash map, and I get some object from the map. Oh, it's not there. Well, I'll create it and add it. Well, all of a sudden they've got a collision. Those kind of check then act patterns don't work unless they're atomic as well. And compute if absent is what people really wanted. So Java 8's made it quite a bit easier. We really like copy on array set and copy on array list. The reason is that if there's something that we have that we're not updating frequently, these are a lot lower overhead than the general concurrent hash map and list utilities. But they have great iteration properties, and essentially each time you iterate them, a snapshot is taken, and you have safe iteration, whereas you wouldn't have that with something like a synchronized array list or collections synchronized list on an array list. So the copy on ones become very useful if you do any kind of low amount of mutation. If you're constantly modifying the collections, they can generate extra garbage, but as long as your mutation rate's pretty low, they're very useful. We don't really go out of our way to switch from synchronized to the Java util concurrent lock, etc. If we don't have to, you only do that if you need conditions, or you have to use, or you want to do speculative locking where you want to say try lock, but only get the lock if I'm done. Synchronized has the problem in that it doesn't, you're stuck forever once you've called the method and entered the synchronized block. You don't get to give up, whereas lock provides that opportunity to do so. Oops. So don't write your own thread pools. If you have particular threads that are, or consumers that are using thread pools heavily, you may want to give them their own pools. An example for us was we had to give Jetty its own pool. It couldn't share our global pool because if somebody did something like spam it with curl, it would check out all the threads from the pool, leaving none for executing anything. You have to manage your own task queuing when you're doing thread pools. It's an important consideration to think about. Having just an unbounded queue is not generally the best solution. I think we're out of time, unfortunately. I ran a little long, so I didn't quite get to my last slide, but thank you very much.